Okay, so the way the rest of the semester, these next couple of weeks are going to work is this. You're going to have another cadence assignment on Thursday. This one is going to be a lot more ILS based, and there's nowhere near as much coding this time around, just because I wanted to make sure you're going to do everything up in some of the memory units and some of the sequential elements. It's going to help reinforce some of the concepts from memory addressing. But everything after that would involve the actual design of the full architecture, and we won't hit that on exam 1, so you're not going to be doing that. So basically, you're going to be going through, you'll have the time during lecture and for the rest of the weekend to go through the ILS courses, do the problems. It's already uploaded, so for those of you who are go-getters and want to get it done sooner, feel free. But there's going to be a little less coding this time around. The next week after that will be dedicated to the exam. The exam is going to be a week from Thursday. So what's going to happen is on Tuesday we'll do a review. The review usually doesn't take very long. I post the take-home portion. I'll go over more detail, but the take-home portion is basically my way of being able to quantify into the exam your study effort, and then there's an in-class portion that represents your review, basically your in-class interview, which is problems that are very similar to what you just saw here. There's also, I found a job, but after that's been posted, that after you complete this course, you'd actually be eligible for. So you can, so I have a video for you to help you present a resume. I have a resume format that Intel gave me. That's like, this is their preferred resume format. I show you how to actually build that up. So you'll do that, and so that portion is you'll apply for the job. Then the take-home portion is you preparing for the job interview, and then the in-class portion is you actually kind of preparing as though you're interviewing for the job. Okay, so but we'll go over that in much more detail next week. So yes, we will go over that in much more detail next week. So for now, we'll just focus on getting through section 3. Okay, does anybody have any questions specifically on previous stuff in the section 3 from the from lecture notes? Okay, so in the previous Tuesday, we went over average memory access time. So we went on one level of cache, and so we're going to start here. How do we actually start building up from there? So we have a level 2 cache, and so what we have here is the hit rate for the time to access the cache plus the miss rate times, and then so you can start seeing the brackets in your hit rate times the access to level 1 and level 2 caches. As I went over on Tuesday, or last week, you have to hit level 1 and level 2. You're missing level 1 and it's there in level 2. And then from there, the next is miss rate for level 2, and then level 1, level 2, and then memory access time. So that's 2 levels. And so you can kind of see there's going to be, we're going to see the 3rd level, and you're going to get the benefit of that. And then for level 3, it's just, and you can see the difference. It's the same thing here for level 2 up to here, right? And then level 3, actually put it in red brackets, and then it's the hit rate to get all 3 levels of cache plus the miss rate times level 1, level 2, and level 3 plus the memory access time. So you can see it's, how many of you have taken a probability course? Okay, so a couple of you. So you remember probability trees, we have this idea, okay, so I have one where I actually find it in level 1 cache, and then I have a miss probability, level 2, level 3, and then that's memory. Right? But in each one, the difference is you actually have to check the actual level of cache in order to go down there. So basically what this is going through here, that's why we're kind of hit on hit rates and miss rates and presented them as probability values between 0 and 1, because that allows you to actually calculate the average memory access time by knowing the probability, and that's typically calculated through the operating system or by using performance metrics. And so a lot of these numbers are numbers that you'll know, and then you'll be able to calculate the average memory access time over a program or a set of programs. So example questions 3.3 and 3.4 kind of show what's going on here. So before we do that, I want to remind you that the level 1 was 10 nanoseconds, right? So level 2 cache, we're kind of doing the same thing from example 3.1. Example 3.1, except in this case we're adding a level 2 cache with a hit rate of 85%, and that access time is 7 nanoseconds. So level 1 cache is very fast, it's 5 nanoseconds. Level 2, the hit rate is 85%, a little slower, and then you're going to see that in level 3 it's even a little lower than that, it's 80% in 10 nanoseconds. So here what we're doing is the hit rate is still 95%, and the level 1 cache was 5 nanoseconds as in the previous problem. The miss rate is going to be 1 minus 0.95 because you miss it only 5% of the time. And then that's where these brackets come in. And so it's the same equation. Here, 0.85 is the hit rate of level 2 cache. And that's times 12 nanoseconds, and that's because that's 7 nanoseconds plus the 5 nanoseconds from level 1, right? Because we have to look at level 1 and then we look at level 2. And that's why it's TC1 plus TC2. And then to go to the last part, it's minus 0.85, so we miss 5% of the time level 1, and then of that 5%, we miss 15% of level 2 cache. And then it's 5 plus 7, which is 12, plus from problem 1, the memory access time was 100 nanoseconds. So that comes out to 112. And from there, we just plug it into a calculator and it comes out to 6.1. So there we had it 100. If we were only accessing memory, we had one level of cache, we get 10 nanoseconds. And now we have 2 levels of cache and we've got that down to 6.1. But you see the trade-off was we're starting to add more hardware. And then likewise, level 3, we do the same thing. Plug it into the equation. We do the same thing before, 0.95 times 5 nanoseconds. We miss 5% of the time. 0.85 times 5 plus 7 gives us 12 nanoseconds, plus 1.085 minus 1 minus 0.85, that's the miss rate. And then we get to the hit rate here. So in this case, for the level 3 cache, it's 80%, so it's going to be 0.8. And here, it's 22 nanoseconds. So we have 5 plus 7, 5 for level 1, 7 for level 2, 10 for level 3. 5 plus 7 plus 10 is 22. And then 1 minus 0.8 comes out to 0.2. That's the miss rate of the level 3 cache. And then 5 nanoseconds, 7 nanoseconds, 10 nanoseconds, 100 nanoseconds, because on a miss, a level 3 miss, in order to access memory, you have to try to read all 3, and they all fail. Then you go to the memory, and that's another 100. So you add that up, and it comes out to 5.575 nanoseconds. So in last Tuesday, when we discussed this, I mentioned that there's a reason that we only end up having 3 levels of cache. One, you're probably happy about that because you don't want to keep adding this on to level 4 or level 5 on an exam, right? You're going to have a level 3 problem on your exam. But if you look at it, you have 100 nanoseconds. If we did a chart here, and then we bring it down to 10, and then we brought it down to 6.1, and then we brought it down to 5.75, right? So you got to see that the return decreases. And so after level 3, you're not really getting much gain, but you're adding a lot more money, right? So basically, it's a intuitive, you're combining the rate of change and how much money you got to put into the computer. So that's why generally after level, most computers will have 3 levels of cache. That's kind of the sweet spot. Okay, does anybody have any questions on this before I move on? Yes?
Isn't there a parenthesis in
yeah, that should be here. Should be, yeah, you get the,
And then inside that little parenthesis, you have 0.8 times 22 nanoseconds.
What do you mean?
Wait, never mind.
Okay. Basically, if you follow this equation, you see how there's a second bracket here? So that should be here. I mean, technically there could be, yeah. No, actually, 1.5 plus, oh yeah, so here, no, the brackets are correct. Again, it's the same thing. If you start getting confused on level 3, kind of do that same thing. Okay, so you have the bracket, so this is 0.95 times 5 nanoseconds, right? So then here, this is 0.05, 5 plus 7, right? So here, that's what you have to do no matter what. So then, but here, in order to go down to level 3, it has to be 0.85, because it's, I'm sorry, it's, yeah, it's 85% hit rate times that and keep going on there. So it's a probability tree. If you start getting confused, draw it out like that. But basically, after developing a few practice problems, you'll get the hang of it. Do you see how that makes sense, though? Kind of intuitively how that contributes to the advanced visual system. All right, so how do we control the miss rates of a cache? So I've kind of alluded to this whole idea of 0.95, 0.85, 0.8. We got hits rates, miss rates. We have all these different block sizes. We know that the block is the minimum amount of information we can pass between different levels of a cache. And we talked about this principle of locality. That's another thing that will be on your exam. And so how do we take advantage of the principle of locality in memory, right? So you have this idea where you can increase the block size to match locality size, right? So what's the challenge on this? What are the trade-offs? If I bring, remember how I gave that example last Tuesday about I can switch people in and out from different rows? If I increase the block size, that means that I would have more people in the first row, right? And then I'd have to have even more people in the second row, so everybody's kind of closer and knows hiding from me in the back, right? So the challenge is you actually have to physically accomplish that. And that's why you're starting to work on the Verilog, right? You wrote up code for a memory element, or you're going to be running up code for a memory element in the next lab. So you wrote up the code for a driver. It actually generated registers and nets. Remember that, all the printouts? So it's actual physical details. So the more you have to swap out, the more you're actually doing in any given moment. And any swap has to be the same. So if I had my memory element where I'm only using this much memory, just this one here, I still have to swap out the whole thing every time. So that's a pro and a con to a trade-off. So increased cache size to increase most data. What's the challenge with increasing the whole cache size? Yes. If you want more cache, you have to have more cache. Right? Someone just busted out the pun gun. All right. So in order to discuss all these different trade-offs, there's 3 different things we're going to talk about when we actually do a swap. How big are we swapping in? How much are we correlating to? And what are those memory elements going to be? So when I put some code in the instruction memory, I'm going to be trying to access a specific memory element, right? And we use that. You remember which type of memory addressing where I'm using a load operation? You get a value from a register, you take the immediate value, you add it into the arithmetic logic unit, and then you go into data memory. When you were in the Navy, you were stationed at a base addressing, right? That's what it's called. So make sure you review that. So this is the whole idea of base addressing. Well, if I'm doing swaps, I still need to be able to take advantage of this byte addressing to be able to know where I'm putting certain things in the data memory. Because the data memory is that introductory to the cache. So so let's say you're level 1 cache and you're one block and you're another block, right? So you're all in level 2, and you have a index that correlates to one another. Meaning that when I swap you out, I'm going to swap you in, that means that the code is now going to be still looking here. Right? And we call that associativity. And we're going to be discussing direct and set associativity in a moment. But in order to understand what we're associating, it's going to be these three terms here. So the index tells me your exact location in the cache. So we formally define it here as a numerical value. It's going to be in binary that's used to indicate the exact value in the cache. So in this case, you guys it would be 0. So it would be there. So tag is a field in the table that contains the address of the information required to identify the associated block. To identify whether the associated block corresponds to the requested data. Now this will make a lot more sense when we work through an example question. But let's say I have memory element 31, right? So in this case, it's 11111. Now I have an index and a tag, right? So if I have two-way set associativity, that means that it's going to have 2 bits to correlate which values I want. So if I have 8 blocks, I use this as my index and this is my tag. So I can have 31 if I have 7, right? And I need to swap in 7. I would swap 7 in here to the specific index, and then the tag becomes 00. Does that make sense? So the tag would be its home. I mean, the index is kind of home, but tells me specifically who's living in there at the given moment, right? And then the valid bit basically tells me whether or not it's actually been written to, right? So a field that indicates the associated block in the hierarchy contains valid data. So we start out, we start up the computer, we have a cache, we have nothing in there. The computer says, I want something from here. Actually, let me do that. The computer starts out, it's empty. The computer says, I want something from here at this chair, right? There's no valid data here. There's nothing there. It could be all zeros, it could be all ones. It's whatever it was when the computer shut down. I need something valid, a valid bit, to tell me whether or not it's actually being used. So the valid bit says, hey dummy, there's nothing there, don't use that. So that's what the valid bit is. You need an index, you need a tag, and you need a valid bit. Yes?
So when the computer shuts down, will it change the valid bit to say when you start back up, it won't?
The operating system, when it starts up the computer, will say, it's like when we take out think of a swap as the previous class leaves and you all come in, right? The operating system would make sure that the valid bits are all updated. I wouldn't say, because there was a woman sitting in the back seat, right? It would be super weird if I was just asking the seat questions. Okay? But if the previous program, the previous class, had a student there, the professor could be asking if that would be valid. I have to then update and say, okay, well, we have 23 students and they're sitting in these specific chairs, and so I can only ask people in those chairs because those are where the people are. Otherwise, that's when they start calling me out to the loony bin. So in this specific case, the operating system takes care of that. Any other questions? All right. So first we're going to go over direct, and then we're going to go over two-way set associative. So the example of what I just showed you of that swap from 7 to 31, that's an example of a direct mapped cache. A cache structure in which each cache location is directly mapped to exactly one location in the main memory. So in that specific case, I use the index to be able to tell me that location. And so the size of the tag is going to be log base 2 of the memory over the block. And for those of you who are going, oh no, logarithms, everything in here is binary value. So if you have some sort of main memory that's 2 to the 10, and your block is 8 bits, right? So that's just 2 to the 3. that just becomes 10 minus 3, which is equal to 7. And then the size of the index is how many blocks I have. So in the example that I gave you before, I said there's 8 blocks, right? So there, it's 8. And then what's going to end up happening here is that it's just 3, right? So what I gave you is I gave you an example where there's 32 bits, right? And for some reason that's there's 32 words in there. And then in this specific case, how do we actually figure out the tag and the index? Well, 32 is 2 to the 5, right? So that's the memory. And then I said there were 8 blocks, right? So I have to have 8, and then there's 32 out here, which I can swap in any given value of 8. So what I do is I have log 2 of 32 divided by 8, which is really 5 minus 3, which is 2. And if you remember from that example, when I had the value of 31, and I said these 2 bits right there, that's this value. And so on the exam, when we do direct and maps set-associative caches, that will be, the size will be 32 bits. And you'll be able to figure out that way. In the index, we had 8, so that just became 3. So that's why the last 3 bits was the index. Does that make sense to everybody? Awesome. Okay, and then this is a diagram where I actually showed just the exact thing here. So here, 001, remember that's our index. So anytime any value that ends in 001, so that could be 1, it could be 9, right? It could be, see, that's 16 plus 8 is 24, 25, right? Anything that ends in 001 will be swapped in here. If there's a current, if nothing's being used, see these that are empty right now, valid bit is 0, right? If you swap something in, valid bit is 1. So the valid bit doesn't just say whether or not it's actually valid, but it tells me if I want to bring in 9, right? Well, do I have something in there already? I look in there, yes it does, it has 1 in there. So therefore, I have to perform a swap. So that's how I actually figure out whether or not I have a cache miss or a cache hit. So if I say, all right, let's just say, for example, you're 0 and you're 1, right? So I want 1, and then I'm the program, and then I want 1 again. Cache hit. If I want 1 and I want 9, right? So let's say Shelby is 9. I have to, okay, I want 9. Well, first thing I have to do is I have to look at the index. Is anyone in the index? Valid bit. Yes. Who's there? Is it not, are you 9? No, you're not 9. You're 1. Then I need to swap you out, put you back into main memory, and then bring 9 back in. So that's how that works. Okay, so just a kind of a fundamental example to see like a bigger memory that you won't necessarily see in an exam, but you would see in an advanced digital system. You have a memory of 16 kilobytes where the block is 1 byte and a cache with 256 bytes. Determine the length of the index and the tag in a directly mapped cache. So in this specific case, 16 kilobytes, and as you get more used to dealing with advanced digital systems, you'll kind of more intuitively know that 16 kilobytes is 10 to the 14, and the reason why, 16 is 2 to the 4, right? 1024 is 2 to the 10, so 16 kilobytes just becomes 2 to the 14. That's just something because I've been working at for years. I'm more familiar with it, but I would highly encourage you to kind of get more intuitive with that. So the block is 8, right? I'm sorry, is 200. I'm sorry, it's 256. So that becomes log 2 of 256. 256 is 2 to the 8, so that becomes 8. So then the size of the tag, using our equation, is actually just 14 minus 8, which is 6, right? So the tag, and then you have the index, and then the memory is 8 bits, so each memory element is a byte in this particular problem. In MIPS, we have 32 bits, so each memory element is going to be a word. That makes sense? It's kind of a straightforward, kind of just reinforcing the same principle type problem. Okay, 3.6. Okay, so this is where we kind of start getting into more how do we actually swap all these in and out. All right, so the type of problem you'll have on an exam is you'll have a direct and set associative cache to compare. In this case, we're going to start out with direct associative. We're going to then do a set associative, and then we're going to do a problem where they're put together. Now, students come up, kind of like with the multiplication, students come up with their own way of making sure that they demonstrate what they're doing. The first thing is I'm going to give you a set of numbers, like here in this case it's 22, 26, 22, 26, 16, 3, 16, and 18, right? What I want to do is I have a cache of eight words and the address, these address references, and show the sequence for accessing the cache. So in this case, you are permitted to assume on an exam that it's 5 bits. I won't give you a number above 31, right? So that means the memory is 5. If it's 8 words, that means that your index is 3. So you have 8 words. I can have no more than 8. I have 32 in main memory. I can have no more than 8 that are swapped in and out at any given moment. So what's going on here is that, and the set of numbers you're going to have, so the example questions that you'll have here in practice are going to be a little bigger, so you have a few more numbers that you need to translate than you will on the exam. I understand there's time constraints. I'm basically choosing numbers because I want you to practice converting them to binary. So here you got 22, 10110, 26, 11010, 16 is 10000, 3 is 00011, and 18 is 10010. Now, when you start doing on an exam, you're going to see some patterns. You calculate the index, and you can see that certain numbers correlate to each other, right? Some of them, this one, you know. So the key thing is that you're going to see them correlating, and you see that 26 and 18 have the same thing, right? So what ends up happening is this is the access, right? So initially everything's no. So you have a cache miss. So I'm including more detail here on the lecture notes than you'd be expected on an exam. What I do need to have is I need to have a final table and a description of whether it's a hit or a miss, right? So what ends up happening here is initially I call 22, right? My valid bit is 0 because I look at 110, right? It's invalid. So what the answer is going to be for that first step, it goes yes. I go to the tag, it's 10, and then it would be memory of 22. So you can do it in one of two ways. Most students, to save time on an exam, would just write memory of 22. That's acceptable on the exam, right? So, and as we see here, as I scroll down, you can see that that is exactly what we've done. I've changed the valid bit from no to yes, and I have the tag correctly and the memory element. Now in this specific case, since nothing was there before, it's a cache miss, right? So what students will typically do on direct memory, and I've given an example of a common student approach, is they'll just underline the index to keep track of everything and write a miss. And so now it's 22, right? And then it's 26 is next. So then 10110 is a hit. What did I say hit there? Oh no, so the next step. So okay, so this was 22, right? And so 26 is 010, so this gets changed to yes. That becomes 11 and then memory 26, right? So next one, and let me go up here and show you all the numbers again. 22, 26, 22, and 26 are the first 4, right? So here, this is a miss, and then we have a hit for 22 again, and then 26 is a hit. And now I'm 16. There's nothing in 000, so it's a miss. And then next I go to 011. That is also a miss, because it's 3. 16 is 0. It's a hit. Here I have 18. It's 010, right? So I have a value in there for, that's 26, right? Since I have to swap it out, I have to put 16 back in there. So so this is 18, miss, swap out 26, right? Does that make sense? Yes, no?
According to your chart, how do you know if it's a hit or miss? 0, 1,
Let me ask. Let me ask you by asking you the same question. How do you know?
Well, I mean, as far as just looking at the chart or whatever, I understand that 22 has the.
So what's the index, right?
Yeah.
0, 1, 0. So this is 26, right? So what's happening here is that 26, you go to 0, 1, 0, you write yes, right? And there's the tag in there, and it's memory 26, right? So how do I know, given that information, if it's a hit or a miss?
So it's a miss if there's nothing currently in that position.
Correct.
But if there is something, it's a hit because you're actually hit to get something else and have to replace it?
No. It's a hit if the element that you are looking for is there. So for example, this is a hit because, this is a hit because 22 is in there already, right? So I want to access 22 again, a valid bit. The tag also matches. In this specific case, miss and swap, I have a valid bit in 101, right? So in this case, it's 26, so it's 11, right? Then I check the tag. They don't match, so it's a miss. Because the actual memory element and 26 and 18 are two completely different values. So it's like, are you 8? So if I tell you, here's the way I would do it. All right, you are 26. Right? And then I come back in, and I know that where you're sitting is going to be the last 3 digits. So I come back and I'll go, are you 18? No. You're in 18's home. Right? Because of the last 3, the index. So what I have to do is I have to go to 18, right? I have to run this in back. That and swap it here. So you're missed in that case. Sometimes I ask students the questions back because I think that they kind of have the pieces together and they allow them to put together. Yes?
So at that point, when you swap out the 26 and replace it with 18,
correct.
If you would have another 26 after that, was that 26 be a miss also, and replace that 26 with a new?
Yes, and you are describing a very specific phenomenon that's in operating system known as thrashing, right? So this is a big problem. It's a little outside the scope of the class. So the question is, what happens if I were to just have 26, 18, 26, 18, 26, 18, 26, 18, right? Yes, I would have to swap it out as a cache miss, swap, cache miss, swap, cache miss, swap. This is why we take advantage of locality. This is why we want code that's close together to be repeatedly used. So that's why we take advantage of temporal and spatial locality, because what I don't want is, it would be extremely annoying if half of it is just swapping out T and Carl the whole time. Right? That if you have something where you're doing more swapping than actual computational instructions, that's known as thrashing. So the one you just hit on, that's an actual big problem in operating systems. So, but you are correct. That's a miss. That's a thing to bear in mind. So specifically, that's why I kind of have. If you look at the question, you'll see that are certain things that I'm kind of re-hitting. Okay, so I put in 16. I have 16 again. That's a hit. So I have 18 and 26. So you see how the problem's kind of set up that way. So I'm testing. Can you actually identify a hit or a miss, which is why I asked the question back to you, because I want to kind of you to think about it a little more that way. So this is the final table. So most students will actually draw this out because they'll keep track of the last 3 digits. They'll say, okay, well, the last 3 digits here match the tag, so it's a hit. So this is the 26, 22, 26, 16, 3, 16, 18. So the 18, that's where it's miss and swap out. So if we look at the actual final table, we have 0, 1, 0. The tag is here, so it's 18, and it contains whatever memory was in the 18th memory block in data memory. Does that make sense? Because this is the faster one. This is the faster level cache that we're swapping out of data memory. And to kind of reiterate what your question is. Remember I talked about how trying to access data memory can often take 100 nanoseconds as opposed to the levels of cache. So the data memory, if we're doing that, it would be 100 nanoseconds, 100 nanoseconds, 100 nanoseconds, as opposed to the very fast computation. So you can see that becomes a big problem pretty fast. All right, so in this case, the final answer, because I had 16, was the last one with the 000 index. It contains memory value of 16. 001 was never accessed, so the valid bit is no. 010 contained 18. 011 contained 3, so it's a yes. And then all of them are no except for 10110, which was 26. I'm sorry, which was 22, which is there. Yes.
So once you get it, does it change the valid bit back to no? Or
No. It's valid, because if you have a hit, it's still there. The only way is if you take something out and don't put it back, which is typically only done when you completely swap out and start a new program or you turn the computer off. Yes.
Based on that chart right there, you've got the unused memory banks, basically.
Mm-hmm.
Instead of swapping out, taking the time and energy to swap out one for one, why couldn't you use the unused ones?
Which is why we're going to get into two-way set-associative cache.
Okay.
Bingo. There you go. So instead of having 8, why don't I just split it into halves, so that way I can have 2 per index to swap it out. So then you can reduce the hit penalty. So the answer here is, we define that as set-associative cache. It's a good sign that you're thinking about things the right way if you're asking the questions either on the next slide or on the next page. That's a good omen. So set-associative cache, we formally define that as a cache structure that has a fixed number of locations where each block may be placed. So we define an n-way set-associative cache as having n locations for a block. What we're going to be discussing in this course is what's known as a two-way set-associative cache. You can think of direct map as one-way set-associative cache. It means we have 8 blocks, there's one index, and that's it. Right? And so I'm going to scroll down here to the example question. So in this case, we have a two-way set-associative cache. So instead of having one block with 8, we basically have 2 blocks of 4. And so to hit on your point, we would be able to put in 18 and 26. So what happens when you have 3 of them? Because we have that the 4, because there happens when you need a third one. That's when you start running into some issues here, which we'll go over in a moment. But here we have given a two-way set-associative cache with 8 words, and the address references, it's the exact same address references. Show the sequence for accessing a cache. And then getting back to your question, assume the cache is initialized as empty, so that way they're all no initially. Draw the final cache table. So in this specific case, we draw them all out. We have 22, 26, 16, 3, and 18 as before. And I'm trying to leave that up there. I don't think anybody's copying down the definition. So we have 22. So in this case, the difference is we split them in half. So the last 2 are the index, but we have 2 that have 1, 0. The last 2, see, 22 and 26 now match, and so does 18. So what happens is 22 is put in, right? So 22, the last one's 1, 0. This becomes yes. Tag is 101, and that's memory of 22. And then next one is 26, so that's also 1, 0. So it becomes yes, 110, and then memory 26. And then 22 and 26 are the next 2. So 22, 26, 22, in this case 16 is the next one. But if we had 26 like the previous problem, that would also be a hit, right? And so by taking advantage of the principle of locality, what we'd be hoping is that 22 and 26 are what we're going to be using a lot, right? So that way when you get this 95% hit rate, that's because we're initially filling the cache, and then we constantly use the ones that we have in that specific 8 value. So then 16 is a miss in this case. 16 has 0, 0, so then we go yes, 1, 0, 0, memory 16. 3 is a miss, 3 is 0, in this case it's 1, 1, right? So that becomes yes, 0, 0, 0, memory of 3. 16 is a hit because it's in there. And then we get to 18. So in this case, we know that 18 also ends with 1, 0. So we have both of our set with 16 filled, right? And then we have to decide which one. So I don't want to go into too much of why this would be the case, but in operating systems, and you can tell when you start doing the advanced usual system, you start hitting on operating system types concepts. But here, this concept I have is LRU. That stands for least recently used. You want to swap out the least recently used one. So in this case, we put in 22, 26, and then we hit 22 again. So the reason why I left out 26 in this second portion of the problem is to emphasize the concept that 22 was most recently accessed as a cache hit, and therefore 26 is the least recently used. So therefore we swap out 26 and then we put in 18. Does that make sense? All right, so now I'm going to show you the final table. What we're going to do in the first lecture next Tuesday is go over the final table. I have a problem there. That will be where exam 1 material ends. Then we'll do a brief exam 1 review, and then we might start going into section 4. So in this case, you can see that we have these values in here, that we have 18 swapped out 26, and we have 22 there. Right? All right, so Thursday, you got to turn in your assignment. I will hand back your quizzes so you can use them to help you study. And then you have the full lecture to do all of the cadence work. The same thing as before. It's due on Tuesday. There's less coding, but more going over material. The material is going to be reinforcing memory accessing, kind of the same concepts that are in the memory addressing that you did before. So I'm kind of timing them out in order to correspond with reinforcing concepts that you'll need to understand on the exams. So on that note, it's 10:45 and you're dismissed.